Welcome back. This is Fundamentals of Micro and Nanofabrication. I'm Swayam Prabha from IIT Bangalore, and today we shall talk. We'll take an example of a successfully integrated product, which is silicon solar cells, and understand how it's made. The reason I've picked silicon solar cell over other technologies is it's a very unique process, in a lot of ways very different from the typical semiconductor fabrication systems. So very different from, say, CMOS, or very different from BiCMOS or any such process. So A, I wanted to give you a flavor of how that is done. B, I wanted to highlight the importance of certain things like throughput, low cost, and how those things are integrated in what traditionally has been a very expensive process. So I think silicon solar cells have made remarkable progress, or have helped make remarkable progress in how to do microfabrication cheaply, and I think that we should appreciate that a little bit. So let's get started. So this is not a device course, and I don't want to spend a lot of time on thinking about or explaining how a solar cell functions. For the purposes of this lecture, it is safe to understand the following. Number one, all solar cells are fundamentally diodes. Right? So if you are from electronics background, or if you have ever looked at any electronic device, you would know that one of the basic electronic devices that we can make using junctions is PN junction. Right? So silicon solar cells are also PN junctions. The only difference is that they are PN junctions made optimized for light absorption. So typically one of the contacts is either semi-transparent, or it is completely transparent, or it has a metal grid, something that allows light to enter the cell and be absorbed in silicon. So that's point number one. The other thing is that an efficient solar cell tries to reduce recombination losses. So one photon would give you an electron and hole, and the efficiency of the solar system, solar cell, depends upon how many of those generated electron and holes can you extract out from the device before they recombine within the cell. So there are a lot of internal recombination processes that can happen. They can happen in the bulk, they can happen at the surface, and the goal of a successful device is to make sure that those recombination processes are either very little or don't happen at all. Okay. So I'll actually start with what would be an end of a device course, which is that I'll give you the most efficient silicon solar cell that we know how to make. So this cell was demonstrated in 1991, and as far as homojunctions are concerned, so if you don't use other materials, if you just stick to silicon, this is the most efficient silicon solar cell we know how to make. So first up, you can see that it looks slightly different. You must have noticed this inverted pyramids here. So the structure, the surface is not flat, it is inverted pyramids. You would notice the fingers. So these are made of metal, which is reflective, of course. So all these metal portions reflect light. So most of the surface is not covered with metal. So there is no blanket metal layer on top, there is just fingers. Of course, you need some metal so that you can take the charge, you can extract the current out. But typically the ratio of the solar surface that is covered with metal line is no more than 5%, maybe sometimes even less. Okay, so in general, you want to keep the metal covered portions as small as possible. Other thing you would notice is that we are starting with a p-type substrate, and this is an n-type. This red represents an n-type material, so you can immediately see that there is a PN junction being formed, right? And this PN junction fundamentally is what is responsible for separating carriers and creating energy from light. Now, those are the simple things you would observe. Like if you knew a little bit more devices, you would start observing that there is not just a p-type silicon, but there's another junction here, and that is a p plus p junction. So highly doped p-type and moderately doped p-type junction. Such junctions help reduce recombination losses at the interface. Why? We would not go into details here. It's not relevant. All you really need to know for this lecture is we need a p plus layer on the backside. Now, one way to reduce the recombination losses is to have p plus layer. Another way to reduce recombination losses is to just restrict the area where the recombination can occur. So if you look at this structure, you would see that in this cell, there is a blue film, which is in this case a silicon dioxide, and that silicon dioxide is of course an insulator, but more importantly a great passivator. So at the interface between the oxide and the silicon, there are negligible recombination. So now because of that, the only place the recombination can actually occur is where the rear contact, which typically is a metal, makes contact with silicon. So this metal silicon interface is the only place where recombination can occur. You want this area to be small, but you can't make this area arbitrarily small because again you have to extract the current at some point, so you have to give space for the current to flow. So you can see that in this structure there are strategically located points. If you look at the slide, there are strategically located points where you can extract the carriers. So with this much very shallow introduction into what a solar cell looks like, let us now imagine how we would fabricate the structure. So supposing you are in the PI team and you have been given charge of making this structure, all the dimensions, all the details have been given to you. How would you go about fabricating this cell, right? So we of course know how to make a PN junction. We of course know how to select a substrate. So we start with the P-type substrate. We can probably diffuse an N-type region. Okay. We would notice that there are two diffusion layers. So there's an N plus layer and an N layer. So there probably is gradation. So there is a moderately doped diffusion, and then we need a second diffusion to do the highly doped diffusion. And of course those two are happening at different places. So we probably need to do lithography in the middle, right? So you need two lithography steps. The inverted pyramids are a little interesting to make. You typically would use anisotropic silicon etching. Now if you remember the wet etch lectures, you will remember that when you take the silicon 100 surface and introduce this to something like a KOH or a basic solution, you start getting these facets. And these facets are the silicon 111 facet, which typically is around 54 or 56 degrees with respect to the surface. So you can basically make these pyramids with that 56 degrees angle, and that would give you your structure on the top. For the backside P+, you would of course have to define another photolithography step, and after the photolithography you would open holes in this oxide, and then you would deposit, you would diffuse some P-type dopant in, for example, boron. And after all of this done, you would then deposit the metal on the back, you would deposit the metal on the front. You would have to do one more lithography step to define the metal pattern on the top, and that is how you would make this cell. And that is very close to how the people who made this cell actually did it. However, there is a problem. And the problem is there are too many steps. When you are trying to make something that is like a solar cell that needs to be produced in thousands, not just thousands, millions of quantities, each step counts. Both it counts in terms of time, and it counts in terms of resources allocated to do that step, right? Chemicals, manpower, equipment, consumables, etc. So you want to be very efficient in the number of steps you want to do. You want to be very efficient in how you want to do steps. And the fact that all of these technologies, like whatever process we just discussed, was developed mostly for microfabrication and nanofabrication of the type that Intel and AMDs of the world do it, was the reason this process was very expensive, right? Because Intel reduced their cost by scaling. Solar cells cannot be scaled, right? I mean, there is no advantage of making a smaller solar cell. If anything, you want to make a larger solar cell that can capture more light. So absent scaling, how does a microfabrication process reduce cost? And so the solar cell industry went into a very different direction than the one that Intel and AMDs and other CMOS technologies did, and tried to really zero down that what is the cheapest way we can make this process. Remember, they did not have to do things at the nano scale here. They were probably okay with millimeter scale or maybe hundreds of micron scale. So they compromised a lot on those finer aspects and gained a lot in cost and processing efficiency. And that is the reason that today silicon solar cells are at par in terms of cost with traditional sources of energy. As of today, it is cheaper to install a silicon solar cell plant than to install a coal-powered plant. And that's a remarkable change. And the whole lecture would be dedicated to sort of understand what sort of innovations were used. Okay. So in this slide, I will just again highlight this, something we have already discussed. So here is the PN junction. Here is the N plus contact. So having two diffused contacts allows you to increase the open circuit voltage or the voltage of your solar cell. We see these pyramid structures. So these pyramid structures actually help in trapping the light. So light typically gets reflected from smooth surfaces, light gets trapped on rough surfaces. So here we are deliberately creating that rough surface which enhances light trapping, which increases the current of our solar cell. And the same on the back side, this P plus contact reduces the surface recombination in the same way, in the same using the same physics that the N plus junction reduces the surface recombination. And then we have these point contacts, and yeah, this is the solar cell. Increased voltage and increased current both increase the efficiency. Okay. So by the way, this cell that I'm talking about, that is a record, actually has a record of around 25.4% or so efficiency. Since then, the silicon solar cell efficiencies have been increased to around 26%, but they use something called a heterojunction, which again I shall not cover in this course. So once again, so now you are, say, employee in a silicon production system, and you have been given in charge to simplify the structure. So one of the first things you might want to do is a good place to start rather would be to look at the cost structure, right? So compare how am I making a solar cell today, understand where is the bulk of my money going, and then try to zero in what can I do to reduce the biggest expense, right? So here is an example. So this is what the cost of a module in 2011 was. These numbers have since then changed. The cost of solar cells have fallen 80% since those times. So don't look at the absolute numbers. Just look at the distribution of the cost. So immediately what sort of jumps out to you is the biggest cost of the module, which is what you purchase, is not the margin, it is not making of the cell, it is actually making of the wafer. And to people in this who have done this course should not be surprised. We had discussed how hard it is to make ultra pure quality silicon, how much work it takes to make a Czochralski silicon ingot, how much care do we have to take, how pure the input materials must be, and all of that adds a lot of cost. So it's not surprising that wafers are the bulk process. But if you looked at this breakup, what you would like to do is to reduce the usage of this expensive silicon as much as possible, and that's something the industry has tried. So this again is the IIT PRV. This is a roadmap set up by the silicon industry to sort of project the directions in which they would want to go. So this was published in 2011, as you would see, and so this was what their assumption was they would do down the line in 2011. Now, of course, today we are sitting in 2019, so we can go back and see how well they predicted. So what they really wanted to do, as you can see from this, is as the years progress, they would keep reducing the thickness of their wafer, and of course, thickness of the wafer, reduction of the thickness would increase, would reduce the usage of silicon and reduce cost. Unfortunately, that does not happen. Despite their best efforts, it does not happen. Even today, at least in India, I know most silicon manufacturers are nobody's using cells that are wafers that are thinner than 150 micron. Despite the huge decrease in cost that they were expecting, nobody is really using thinner wafers. And the reason it turns out is that thinner wafers break more easily. So again, if you go back to the earlier lectures on substrate, you may remember the discussion we had on what are the typical thicknesses of silicon wafers. So when Intel does the CMOS processing, a 6-inch wafer is around 700 to 800 microns thick. Intel has that thickness because it does not want any of the wafers to break. So it makes a thick piece of silicon that is a little robust. It can be taken to high temperatures, it can be taken to low temperatures. You can do rapid thermal processing on it without the stresses becoming so large that the wafer breaks. But that was not an option for silicon. So silicon really tried to reduce the amount of silicon. And the only way they could do that was by reducing the thickness. So they came up to around this magic number of around 180 microns. So this was for a 6-inch cell, which is still significantly thinner than what Intel is using, but any more, and they realized that they just break too many wafers, and because the yield is not there, they couldn't go any further. So the moral of the story is cost is one thing, but yield is extremely important. If you are not getting the yield from your process, you have to really rethink, because loss of a wafer is far worse than a slightly more expensive process. The other commercial challenge is to increase the speed or throughput. Now, throughput refers to some version of how many wafers per hour or wafers per second are you trying to process. Now, again, for the CMOS fabrication, the Intels and the AMDs of the world, throughput is important, but the way they increase throughput is by scaling, right? So they try to make devices smaller and smaller, and if they try to have larger and larger wafers, so they are able to process a lot more devices in one batch. Now, silicon solar cells cannot be scaled. In fact, if anything, you want larger and larger silicon solar cells. So absent scaling, what can you do? The only thing you can really do is make sure the process happens fast. right? So each step should take as little amount of time as possible, and you should be able to push as many wafers as possible within an hour. And I can imagine if you have a series of steps, the slowest steps then decides the rate at which you are producing. So this has been known for a while, but again I'll give you some numbers. So here is the cost. These are again 2011 numbers. I apologize for the old numbers. The numbers have significantly changed. They are 80% cheaper now, but the trend is indicative. So if you look at the module cost, in 2011 the module cost was around 89 cents for in terms of dollar per watt. And that was from a US plant that is creating 60 megawatts of production a year. Okay. At that time, large silicon manufacturers had already made huge changes in their processing capabilities, and they were at that point producing around 2,000 megawatts. So this is more than 30 times larger, right? So if they have 30 times larger production, they must have a 30 times higher throughput. And some of that throughput came by just having a lot more equipment, but a lot of throughput also came by really, really careful optimization of the processes. So, and just by sheer volume, by just producing more material, they were able to reduce their cost by up to 20%. And that's a huge deal. 20% in such a cutthroat market is the difference between a company that is solvent and a company that is bankrupt. So, and when we are talking about throughput, how many wafers per second are we talking about? So the 2000 megawatts per year, and you can do some calculations if you assume 30-20% efficiency, some X numbers of hours per day, production, etc., you're looking at a throughput of around 30 wafers a second. I mean, those of you who have worked in a clean room, I would urge you to sit back and think about that number. That translates to 50,000 wafers an hour. It's a massive number of wafers. Now think of the way we are doing photolithography. Think the way that we are optimizing recipes. Think of the way we are doing evaporation, sputtering. Think of the way we are doing dry etching, ALD. Is it possible to actually have this kind of throughput if each step in your fabrication process takes half an hour to 1 hour? Of course it's not possible, because then you would need 30,000 machines, right? If a process takes 1 hour and you need to do 3,000 wafers an hour and you can only 1 wafer an hour, you need 30,000 machines. So the capital expenditure explodes, and at some point it's not viable to do so. So to cut a long story short, throughput is extremely important in any fabrication process. It's more so important in solar cells where scaling is absent. So the only way we go forward is by simplifying the processes, by making things faster and doing the bare minimum needed to get a good device, but not to over-engineer it. So with those thoughts, let us now go into the details of how actually a silicon solar cell is made, and I will keep highlighting the differences in what is done in production than what you have seen in this course and what an Intel and AMD would do. And in all of those explanations, you will see this idea come through: throughput, cost, throughput. What is the fastest way I can do this? What is the simplest way I can do this? All right. So most commercial now silicon solar cells have also of course evolved. There are more complicated versions of silicon solar cells. There are better technologies, but I will discuss only the vanilla simple, what is called aluminum back surface field screen printed silicon solar cell. So this is what the structure of that cell looks like. It's a simple cost effective process. It typically gives you an efficiency of around 17-19% at the cell level, around 15 to 17% at the module level. Okay. So this is what the structure looks like. Now I would urge you to compare this structure with the structure that we started with this lecture with, right? So right off the bat, you see that there are certain things that are common and there are certain things that are different. So once again, we have a p-type wafer, but thinner. That structure actually had a 400 micron wafer, but in this case it's 180 micron. So you see the Y cost. We see that a PN junction that is required. All solar cells have PN junctions, great. But we see that there is only one N-type diffusion, right? There is no N plus NN. And that is to save on one diffusion. One less diffusion means cost saving. We realize that there is no P plus layer, but something called aluminum back surface field. Aluminum is a group 3 element, so at least theoretically it should be a p-type dopant in silicon. It's not commonly used because it's a little lossy, but again, silicon solar cells really wanted to optimize cost, and it turns out for various reasons the aluminum back surface field is very efficient. So we'll talk a little bit more about it later. For now, let's assume this aluminum back surface field is our P plus layer, so that is common. However, one difference in the P plus layer is the P plus layer is continuous, right? It's everywhere. while the P plus layer in the structure that we saw before was confined to some places. Now, why is it everywhere? Because then we don't have to do a lithography step to pattern that, and any saving in lithography is a huge saving in cost. You again see the texturing. We have pyramids. The only difference is we have not inverted pyramids but right-up pyramids. As we shall see, this is an easier texture to produce. So even though it's a little less efficient, this is the one that silicon solar cells do. Okay. The other thing we notice is the size. So we have, other we notice is the front electrode. So once again, we have a front electrode that is part of the, some part of the device is covered with metal. And the thickness of the metal top electrode in this case is around 100 micron, which if you again think of microfabrication is huge. I mean, we are talking about nanofabrication in Intel. We have critical dimensions of 10 nanometers, but that is not the goal here. The goal here is to do what is barely enough, and 100 microns for silicon solar cells is plenty. How do you make these cells? How do you make these? Now, because your critical dimensions are so much larger, you can now imagine that the patterning process can be made significantly simpler, right? And we shall see how that is done using screen printed. So that is why these are called screen printed solar cells. Okay. So with that much discussion, now let's go into the individual steps. So here is the process flow. So we start with a wafer, then you do texturing, cleaning, dopant diffusion, PSG removal, edge isolation, silicon nitride ARC and passivation, rear metallization, front metallization, co-firing, testing, sorting, and finally manufacturing of the module. So now we shall look at each of these steps one by one in the next few slides. So we have already spent a lot of time in the lecture on knowing how to make Czochralski silicon solar cells. So we know how to do that. I wanted to spend, and we did discuss, I think, one slide on multi-crystalline silicon solar cells, but did not go into excruciating detail. So I wanted to spend a little more time about multi-crystalline solar cells. So the structure that I showed you in the previous slide actually can be made using monocrystalline silicon cells or can be made using multi-crystalline silicon cells. Both technologies are currently being pursued. I think multi-crystalline is more popular, but monocrystalline is a little more efficient, and in the last few years has been becoming more popular and capturing the larger market. So we know how to make monocrystalline wafers. We shall not discuss that. We shall discuss how to make the multi-crystalline wafers in a little more detail here. So as before, we start the polysilicon feedstock. You put it in the crucible, and these crucibles are typically a square shaped and made of refractive material, aluminum oxide or something like that. Then you put that in a furnace, so you can actually see, right, the crucible here, the crucible being, and this is maintained in the furnace that is arguably under vacuum, and you push it in. What you are doing here is what is often called fractional crystallization. So you just you melt the silicon and then you slowly cool it down in a slightly controlled fashion. But there is no introduction of the seed, no rotation, no slow pulling, and because of that you don't get a single crystalline wafer. You actually get a multi-crystalline wafer. With some optimization though, the grain size that you get can be fairly large. So this is actually what a multi-crystalline silicon wafer looks like. So these grains can be as large as centimeters or a few millimeters at least. When you take it out of the crucible, the ingot that you actually get looks like a cuboid, right? So, and in general, most common type of wafer that is used for silicon fabrication is P-type. So during this process, you would make it P-type doped. So you get this ingot. You sort this ingot into individual ingots of a certain size. So the most popular size for silicon solar cells is 6-inch wafer, around 156 mm. So this huge ingot is cut into these cuboids where the cross section here is the 156 mm. Now each of these now needs to be sliced into wafers. So the way we do that is through wire sawing. So schematically, I think I mentioned this when we were talking about wafering in the first few lectures, but here I'll give you the images of the actual machines. So this is what the machines look like. So these are the rollers. You see this shiny part on the top and this taunt point on the sides. These are these wires. These are very thin steel wires with impregnated diamond in them. And these very thin wires are actually what cut these cuboids into wafers. So here you can actually see these ingots have been mounted on a holder and it's being pushed down onto these wires and slowly being cut, and each of these slices then gives you this silicon wafer that you can go and use. Okay. So this is what you have. So you can actually have from the square shaped ingot that we had. That's why we started with the cuboid. So you get these square shaped ingots. From the square shaped ingots, you get multicrystalline wafers. Now, if you were to do single crystalline processing, of course, you do this Joukowsky process. So in which case you don't get square shaped ingots, you get cylindrical shaped ingots. Now the problem with cylindrical shaped ingots is that they give circular shaped wafers. And when you attach circular shaped wafers on a module side by side, you lose a lot of area in the middle because circular shapes don't fill a flat area very well. If this is not making sense, give it some time. I'll show you the full module and we shall discuss this fill factor part. So what people do is take that cylindrical wafer and don't exactly make it into a square. That would waste too much material, but they make it into what is called a pseudo square. So it has these sort of rounded edges, if you notice, and these rounded edges give you these sort of pseudo square wafers. It's still relatively squarish, but with rounded corners. So both of these exist. Both of these are often used to manufacture silicon solar cells. These are more efficient because they don't have grain boundaries. These are more cheap because they are faster and easier to make. Multicrystalline are faster and easier to make. Monocrystalline are more efficient and expensive. Okay. Now that you have a wafer, we have to now get started. And of course, the first thing you want to do is cleaning. Now, before cleaning, one thing that the silicon people do is texture it. So as we discussed, light gets trapped on rough surfaces, and you want to create those rough surfaces up front. So what is done is you mount these wafers into these cassette carriers, and silicon solar cells are, as I said, about thousands of wafers an hour type of throughput. So you mount several hundreds of these wafers in these cassettes, and you do all the processing in these large vats of chemicals. So this is what those chemicals look like. So this huge bath is full of a certain type of chemical, and there's maybe a robot or an operator who's taking hundreds and hundreds of these wafers, dipping it in one tank, doing some process, taking it out, putting in the next tank, doing some process, taking it out, etc., etc. Now, how do you make a texture on the surface? Well, you do anisotropic etching. And what we know is that the easiest thing you can do is potassium hydroxide. Now, when we are doing wet etching, I discussed that potassium hydroxide is not a CMOS compatible process. It creates a lot of potassium contamination. That is why it would not be allowed in a CMOS factory, but KOH is allowed in a silicon solar cell factory because they don't care so much about the potassium and the sodium contamination. And so they do clean some of it, but they don't care about the trace contamination. So they use the cheapest chemical they can find, which tends to be sodium hydroxide or in some cases potassium hydroxide, and they dip these wafers in without any mask, without any lithography. The surface gets randomly patterned into these pyramids. So that is what you see here. So these pyramids, and the angle of these pyramids is that same 111 plane angle. And this is what allows you to trap light by just roughening up the surface. Now, if you have single crystal silicon solar cells, this is done automatically because an isotropic etching of the 100 will give you the 111. But if you have a multicrystalline cell, then it doesn't have one orientation, or a multicrystalline wafer. It doesn't have one orientation. And if it doesn't have one orientation, then an isotropic etching will not give you pyramids. So in that case, people do slightly modified HNA etch. So nitric acid, hydrofluoric acid, acetic acid. And this acidic etch creates some amount of texture simply because different facets get etched at a slightly different way. Just to give you a sense of scale, typically these baths are very large and they are maintained continuously. A single bath may process more than like 2 million wafers before it's switched out and used for and replaced with a fresh batch. So these are really vast amounts, really large volumes. Okay. Other than texturing, one more thing that we do during this process is remove saw damage. So right before this step, we did wafer sawing, right? So we took an ingot, we created wafers. There's a lot of surface damage that happens in these processes. So what you do is you have to remove that surface damage. And the easiest way to do that is just etch the surface. So during this texturing, we don't just get the texture, but we also etch the top surface of the wafer to expose undamaged bulk. Okay. So this is the animation. So you have your wafer, you have some damage on the top, damage on the bottom, represented by these dots, and you put them in a KOH bath, and that just anisotropically etches it, removes the saw damage, and gives you this pyramidal structure. All right, let's continue. So once you have done that, then you want to do some cleaning after texturing. You want to remove the potassium contamination, but you also want to remove metallic contamination. You want to remove organic contamination. So how do we do that? In the typical system, we would do an RCA clean, right? So we would start with RCA1, we would have dilute HF, you have an RCA2, you would again have dilute HF. Some of the research labs and really careful semiconductors, really high efficiency solar cell manufacturers may still do that. The problem is this process becomes too slow. Each of these chemical baths is very expensive to make. Because of the H2O2, the chemical will not last for a very long time, so you have to keep replacing it for a whole host of reasons. Practical solar cell manufacturers skip one or two of these steps. A lot of them do not do the final HF. Some of them do not do the middle HF. Some of them completely remove the ammonium hydroxide and only do RCA2. Some of them remove in the RCO2 even the peroxide, they only have HCl. So it really depends upon what works for you, and it depends upon what sort of contamination is there in your process, what contamination exists on your wafers, how clean is your system, then how little of a cleaning is enough for you to not create so many defects that it affect your efficiency. So it's all about a very cutthroat, very careful cost-benefit analysis. Okay. This is what a wafer cross-section would look like. So nothing has changed. You still have the pyramids, but now the surfaces are clean. After this is the dopant diffusion step. This is the high temperature step. This is the critical step. You really want to be careful here. Any contamination on the surface will diffuse in, kill your lifetime, and lifetime is very important to silicon solar cells. So, this step is important. Uniformity and purity and all, from that perspective, this step is important. How do you create the diffusion? How do you create that p-n junction? Now, the easiest thing we can do is diffusion. The more complicated thing we can do is implantation. And of course, CMOS processing has completely moved to implantation because that's what they need. It provides better control. But solar cells have not. And the reasons are again obvious. Ion implantations are too big, the instruments are too big, they're too slow. There were a couple of startups that tried using implantation to create solar cells. They were able to make more efficient solar cells. But overall, for various reasons, I don't know if it's because of ion implantation or the reasons, they were not able to compete in the market. As of today, most silicon manufacturers who are competing in the market use diffusion. Specifically, they use POCl3 bubbler type of diffusion. So the POCl3 liquid, you bubble gas through it, get the phosphorus inside, that dopes the wafer, and you move on. Now, because this is a batch process, right? Because you're doing this in a furnace, you want, in order to increase the throughput, they are massive batches. So here's an example, I think, from Boviet Solar USA. I think there's a production system. So you can see the scale of things, right? So each of these is a furnace. So they have 4 furnaces. Each furnace has 4 furnace tubes, and each tube, I'm willing to bet, can accommodate 200 to 400 wafers each. So you can do the math. Together, if say it does 400 into 4, 1600 into 4, 6400 wafers, and 6400 wafers can be processed simultaneously. So if their diffusion process takes say half an hour, probably takes closer to 60 minutes, but say it takes half an hour, then you can process more than 12,000 wafers an hour in this system. So you see the throughput. Throughput is really, really important. And but still, diffusion is a slow step. It takes at least 10 minutes to make a diffuse film, and you have to then give some time to load and unload and stuff like that. So overall, you need so many systems, right? So because the fundamental step is limited in its throughput, you have to compensate by having a lot of such equipment, and that increases the cost. In this case, the increase in cost is only in a furnace, which as things go is not a very expensive equipment, so it's okay. But if you were to do the same thing, say for an implanter, which is a way more expensive a tool, that would become financially untenable. So that is the reason why sort of diffusion won out over a more accurate or more repeatable implantation. Okay. In terms of cross sections, you see that the boron doped wafer, you see that we have this orange represents the boron doped layer, the phosphorus doped layer that you have created. Because you have not done any pattern, you're doing this on pure wafers, the diffusion will happen all the way across. And that's an issue because you want the p-n junction to be only on one side. So as you'll see, we'll do things to fix that later. Because we are doing a POCl3 bubbler, you also form the phosphosilicate glass on top, that is the darker orange, and that of course needs to be etched away in order to proceed. So the next step is that etching of that phosphosilicate glass. So when you etch the phosphosilicate glass in HF, you are left with this boron doped wafer, this phosphorus doped layer that wraps all around it, a textured surface. That's it, right? Now, since I had some space on this slide, I thought I'll show you what a modern etching system looks like. So the previous etching system that I showed you was a batch process where you load the wafers into cassettes and dip it in one bath, then the next bath, then the next bath, etc. Modern systems, even that is too slow. So what modern systems have started doing is what is called inline wet processing. So the wafers enter the assembly line on the back of this equipment, and internally it has these rollers, and the liquid is filled to the brim of these rollers. So as the wafer goes over these rollers, it touches the liquid underneath, and all the etching or whatever processing you're trying to do needs to happens, and then you see the wafers come out on this. So it's like a belt process. It's like a conveyor belt. Wafers go in, wafers go out, and this can be done at a fairly fast pace in a by using robots without human involvement, and that really increases the throughput, reduces cost, and is the result of a lot of innovation. Okay, so you can already sort of see this is a significant departure of how Intel or AMD would do wet processing, how solar cell does it, and solar cell does it at a scale that is truly mind-boggling. Now we have to now solve the problem of this wraparound emitter or wraparound doped layer, because that we cannot have a device like that. So what needs to happen is, the first thing is that this edge needs to be cleaned off, and the way to do that is they use edge isolation. The more traditional methodology of doing this is in the following manner. So you stack wafers one on top of each other. So these are hundreds of wafers, so you see. So because they are stacked on one top of each other, you are only seeing their edges, right? Only the edges are exposed. So the same thing is shown in this cross section. They are stacked one on top of each other, and only the edges are exposed. Now this whole system is then introduced to some plasma that can etch silicon. But because the only exposed surface is the edge, the only thing that gets etched is the edge. So once you do put this in the system, the plasma attacks, the edge gets etched away, and as the edge gets etched away, so does the wraparound emitter. So after this step, what you then have is you have a boron doped layer on the top, a boron doped layer on the bottom, but these two are not electrically in contact anymore. Now this is the older process. The more modern process these days is, again, they're trying to make things, they're trying to move away from batch processes, move away from equipment where human involvement is concerned, where you have to load the cassette and unload the cassette, which takes time, and every now and then a wafer would break. You don't want to do that. You are moving towards an inline process. So how do you do this inline? You do this using a laser. So you now have tools where, once again, the wafers are sort of going on a belt, and you detect the wafer, there is a laser on the top, you just scribe a rectangle around it, and as you scribe the rectangle around it, you etch away a little bit, you create a groove, and that groove is what electrically isolates this diffused layer from the diffused layer on the backside. And yeah, so that's called the laser-based edge isolation. This is the more modern tool. This is what newer production systems do. So once you have made the junction, then you have to make something called anti-reflection coating or silicon and a passivation layer. Now the passivation layer on the top reduces surface recombination, but it also acts as a way to prevent reflection losses. Now again, I don't want to go into details, it's not a device course. I urge you to read up about anti-reflection coatings if you are very interested. But a thin layer of silicon nitride on top of silicon will reduce reflection losses. So that's why we do it. So how do you deposit silicon nitride? Now we could of course do LPCVD. Typically that requires high temperatures and requires another bunch of furnaces. A slightly lower temperature process would be PECVD, but PECVD often tends to be a single wafer process and requires expensive RF power supply. So what do you do? So there was a lot of innovations that have happened. Some, I think, older manufacturers tried LPCVD, some tried PECVD. Most modern ones tend to use PECVD these days. But again, this is very different from the PECVD that you have probably seen in your research facility or you would see in an Intel fabrication system. These plasma systems are huge. They look like this, so they look like furnaces. They have, again, in this case, there are 4 different furnaces. Each of these is actually an RF deposition system. Now, in order for it to be an RF deposition system, you can imagine it requires electrodes, right? So how do you load 400 wafers and provide electrodes to each of them? So the way to do that is they create these graphite wafer holders. So in each of these grooves, 1 wafer sits. And I urge you to just do the math. There are hundreds of wafers that can be loaded in this one cassette. And this cassette is then loaded. You see, this cassette is the same thing here. Then this cassette is loaded by the robot inside the furnace. The process is started. The wafers are unloaded, and you keep going. And so these sort of, again, optimizations and advances is what allows you to do that many wafers per hour, which otherwise would not be possible. After this process, you basically have a silicon nitride film on the top. So with that, we can come to the end of this lecture, and in the next lecture we shall continue from this point. So we have partly made a silicon solar cell. We'll look at how the rest of the silicon solar cell gets made, and yeah. So see you then.